Welcome again, everyone, to the subject we were discussing earlier. This is part two of the graphs of trigonometric functions. This is the subject today. This part of the video is going to be talking about the subject of graphical transformations. It's really a matter that I would normally leave to my, I was going to say colleagues, but I don't really consider them colleagues, to the human beings who are in the world of applied mathematics. But today we're going to really go away from the lofty realms of proofs and theorems to observe, rather reluctantly, I assure you, I'm doing this reluctantly, to the spectacle of shifting, stretching, and flipping trig functions. So kind of brace yourselves. I'm doing this for a student. I have one of my subscribers is asking me to do this. And I'm doing it for that subscriber because I value their welfare over my own. This should be about your welfare and not my personal self-interest. And probably I can imagine probably the student is a victim. Not sure if this is true, but probably a victim of some teacher who is using the Common Core or imposing certain graphing standards on the student. So basically, we're going to be talking about there's all kinds of shifts in a graph. You have something called, for example, the horizontal shift, and you can kind of think of it. Imagine moving a sine or a cosine wave left or right, almost as if you're encouraging to take a stroll. It's really a trivial transformation, and yet it's apparently vital to graphed functions. You have to shift sometimes your sine wave by a certain number of units, C units, we can call them, and you simply add or subtract from the angle. That's all you're doing. You're kind of pushing it, effectively urging it to explore new territory while remaining hopelessly bound to it still has a periodic nature. That's not going to change in any way. Then you have vertical stretches, right? You have the vertical stretch. That's where you're kind of being cruel. You ask the graph to expand or compress and modifies the amplitude. We're going to talk about those definitions. We're going to get very mathematical in a moment. But I'm just kind of giving you the introduction. And you might say you're kind of dialing up the function's excitement level. Though for one, I see no real need for such dramatics. A sine function, I believe it's perfectly content as it is. And yet we stretch it all the same, all in the name of application. And you magnify each peak and trough as if to make a spectacle out of perfectly reasonable, at least to me, oscillations. And then you've got reflections, right? The reflections where you kind of have to, sometimes they make you flip your trigonometric function across an axis. And it's kind of as if the poor sine wave in an act of defiance or perhaps sheer resignation, decides to invert itself. And we are, in a way, living in an age of inversion, no pun intended. You multiply by -1, and voila, you've got the wave is upside down. And now it oscillates as if in rebellion against its own nature. It's kind of a bit melodramatic, if you ask me, in my humble opinion, but it's effective. Then you have phase shift, which is really a horizontal adjustment. It's urging the graph to start its journey just a bit earlier or later. I suppose one could liken it to politely delaying a lecture, or heaven forbid, beginning it too early. And my students would probably not like that, I'm sure. A minor adjustment, and yet significantly enough for the sine wave to announce its entrance at a more fashionable moment. So there you have it. It's the grand array of transformations that kind of drag the trigonometric functions into new and arguably, I would say, unnecessary configurations. I must confess, as I was kind of thinking of how to present this has been somewhat enlightening in a way, even if the field of graphing remains. And I leave that best to the applied mathematicians and people who have a different use for it. But we're going to discuss, let me see if I can once again share my screen. The first part of this video is going to be a sort of a description, kind of a mathematical description of what the functions are from a mathematical point of view. And then we're going to do the sinusoidal. The subscriber asked me to kind of go over the sinusoidal function. So luckily, I was blessed because one of my colleagues and is very much into applied mathematics and sort of sent me, I asked the gentleman to send me some problems that he said that he gave his students last semester. So I'm going to go by that, but and see if I can explain it from a pure mathematician point of view. So let's begin with something. In the previous video, we graphed sine, cosine, and tangent, but we only graphed it purely. I said sine of x, cosine of x, tangent of x. What if I asked you, and I said, we're going to graph instead 2 times the sine of x, and also we'll say y equals sine of x plus 2. Right, from this perspective. Well, you can produce the graph. You already know, and if you don't know this, you should watch the previous video. You should know that what the graph of sine of x looks like, and you can produce this by what we call scaling the graph of the sine of x vertically. It's going to be scaled vertically away from the x-axis by a factor of 2. And if I could do this using technology, so can you. Because like I told you in my previous video, I am sort of off-grid. And so it's a lot of it's a learning curve for me to use all these new gadgets that they have out there for graphing and all that. Although the TIs were already available when I was a student, but I'm going to produce the graph for you so you can see visually what I'm talking about. All right, you see here what happened, right? The only difference, the solid line is 2 sine of x, and the dashed is the sine of x. And you can see the only difference here between the graph of y equals 2 sine of x and the graph of y equals the sine of x is the vertical. It's a vertical scale. Now, we use, first vocabulary you're going to learn is called the amplitude, right? We use the amplitude, right, of the as a measure of the vertical scale. So the amplitude equals half the vertical distance between a maximal, what we call the highest, and the minimal, the lowest, which is the lowest point of the graph. Or equally, you can say that the amplitude of a sine or cosine function is half the difference between the maximum and the minimum values of the function. So you can see here the amplitude of sine of x by itself is just 1. And the amplitude of 2 sine of x is 2. So you can graph now the second part, y equals the sine of x plus 2, simply by shifting the graph of y equals the sine of x up. And you're going to shift it by 2 units. And it's going to look something like the following. I'll show you here. See if it came up on my utility. Okay, you should be able to see this. So notice that we have here the shifting. When you shift the graph vertically, it doesn't affect the vertical distance between the maximal, the highest, and the minimum, or the lowest point on the graph. So you could say the amplitude of the graph of this is sine of y equals sine of x plus 2 is the same as the amplitude of the graph y equals the sine of x, which is just 1. Right? So I hope this is clear. Now, what if I asked you to graph y equals the cosine of 2 times x? So part 2. Well, if you remember, if you know about functions, you know that the graph of y equals f times 2x in a regular situation is really a horizontal scaling of a graph, right? When you have a function y equals f of x, towards the y-axis, we have a factor of 1/2. So if you want to produce y equals cosine of 2x, you have to scale the graph of cosine of x itself. You have to scale it towards the y-axis by a factor of a half. And so you produce a graph that I'm going to show you in a moment. You're going to see the scaling of 3 specific points on the graph. And I kind of indicated that using gray arrows, but if I can bring it up. All right. So you see what happened here, right? You have the solid line is the cosine of 2x, and the dashed is cosine of x, right? You can see there. Now, what about the period of cosine of 2x? Well, the period, this is very important. It repeats every 2 pi. Every 2 pi, we said. So if you compress, since you kind of compressing this graph horizontally by a factor of a half, you produce the graph that is here, the cosine of 2x. And the graph repeats every 2 pi times a half. Remember, half of 2 pi is pi. So the period of the cosine of 2x is actually pi. And then you have if you think about the period of, let's say I asked you, what is the period of a number? And we'll just say cosine of ax. All right, so keep in mind this graph. And if you think about it, this would result when you compress the graph of cosine of x, you would have a horizontally, right, by a factor of 1 divided by a. You have to 1 divided by a. Why? Because the graph of y cosine of x, y equals cosine of x, we said it repeats every 2 pi. So the compressed graph of y equals cosine of a times x will repeat every 2 pi over a. So you could say that the period of cosine of ax is 2 pi divided by a. All right, I hope that makes sense. The other issue is, what if I asked you, what is the period of sine negative x over 3? Well, you have, first in a situation like this, you're dealing with a negative sign. And remember that we talked about in the previous video, the graph of f of negative x is, remember, it's a reflection of the graph of the positive over the y-axis. So in this case, this is a reflection of sine of x over the y-axis. And if you think about reflecting the graph of a periodic function over the y-axis, it doesn't have any effect on how frequently the graph repeats itself. So the period of sine of negative x, we said, is the same as the period of sine of x, which is 2 pi. Right? 2 pi. Make sure you have that. Very important. Now we have to deal here with the fraction. So if you think about the y equals f of whatever x over 3, you have a horizontal stretching by a factor of 1 divided by 1/3, right? It's 3 away from the y-axis. So this here results from stretching the graph horizontally by a factor of 3, right? The 3 is your factor here. And since the graph of y equals sine of negative x, or sine times negative x, repeats every 2 pi, the graph here repeats every 3 times 2 pi, right? That's your factor here. And 3 times 2 pi is 6 pi. So your sine of negative, the period of sine of negative x over 3 has a period of 6 times pi, 6 pi. And you can follow the same reasoning when you did from the previous problem. And both the sine of ax and the cosine of ax is 2 pi over the absolute value of a. And a, of course, remember, has to be a non-zero constant. Makes sense, right? You cannot have 0 in a denominator. There's 2 pi over a. All right? And what if I asked you, if we're dealing with, let's say, sine of 3x, well, let's do a function, actually. We'll do 3x over 2 plus cosine 2x. And if it is periodic, what is the period? So think about that for a moment before you listen to me. Just pause the video and think about it. All right, now that you've paused the video, we start with the graph of, first of all, of this 3x over 2, sine of 3x over 2 plus cosine 2x. We need to check if the graph repeats itself regularly. Of course, you wouldn't want to build such a graph. Not even I would try that by hand. You'd use a computer like I did, and you are going to produce the graph that as follows. I'm going to show you what it looks like. All right, hopefully that you can see it. So the solid line is the sine of 3x over 2 plus cosine of 2x. And the dashed line is y equals sine over of sine 3x over 2. And y, the dotted line, you should be able to see the dotted line also, very faintly though, but it's, I don't know why it came out like that, but y equals cosine of 2 times x. So you can see that the solid graph appears to peak at x equals, if you look at negative 5 pi, it peaks. And then you have x equals negative pi, and also x equals 3 pi. Have you noticed a pattern here? Each peak is 4 pi after the previous peak. So that you have the pattern of the solid curve. You have x from x equals negative 5 pi to x equals negative pi. You appear to be exactly the same as the curve if you compare negative pi on the graph all the way to 3 pi. And the pattern appears to continue after x equals 3 pi. It looks like a graph that is, of course, repeating itself. So we can suspect that our function here, sine of 3x over 2 plus cosine of 2x, is periodic. But can you be sure? And if it is periodic, why is it periodic? Well, look at the large peaks here. That gives you kind of a hint. The peaks appear to occur where we have here both sine of 3x over 2 and cosine of 2x equals 1. So you have to kind of investigate the sine of 3x over 2 and cosine of 2x separately. And you have to pay special attention to on what the values of x make either equal to 1, both equal 1, well, both equal 1 at x equals negative pi. And as x is increasing, the sine of 3x over 2 again equals 1 after it has gone through a full period. So one period of the sine of 3x over 2 has a length. Remember, you have to divide it by 3/2. It's 2 pi divided by 3/2. So you have 4 pi over 3. So the sine of 3x over 2 equals 1 when you have negative pi plus 4 pi over 3. And I put this in a notation when I was doing it on the computer so that you can all have it, because it's one thing if I say it, but if I put it on paper, you should be able to see. I'm going to put it as a note for you so that you can pause the video and kind of copy it. See if it works. I had to do all these mathematical symbols, the pi symbol. Let's see if I can. Okay, so it did come out, right? So if you want to copy this so that you have it as a reference. Now, also you have the cosine of 2x, right? Now the cosine of 2x has a period of 2 pi over 2, which equals pi, obviously. So the cosine of 2x equals 1 when x is equal to 0. And it also equals 1 at So at 0, at pi, at 2 pi, at 3 pi, and so on. So both of them equal 1 again at 3 pi. And now you have an explanation for why they will both equal 1. Again, at x equals 3 pi. Well, 3 pi plus 4 pi is 7 pi. And as x is increasing by 4 pi, it goes through exactly 3 full periods. And the cosine of 2x goes through exactly 4 full periods. So if you increase x by 4 pi, you have both the sine of 3x over 2 and the cosine of 2x are unchanged, right? So we have a periodic function, right? Now, the phase shift of a function is always going to be in the following form. It's you have the phase shift, and that is the sine of x minus, let's say, well, we could do, the form is typically f of x equals a times the sine and it's going to be times or parentheses bx plus c. And bx plus c. And we have a situation here where, well, a, b, and c have to be constants. And that is the smallest horizontal distance by which the graph of g of x is equal to a times the sine of bx. And it must be shifted to produce the graph of f. Now, you typically use positive values for the phase shift if the shift is to the right, and of course, negative if the shift is to the left. So I hope that that cleared up that part. I mean, there's a lot more to say, obviously, but hopefully that that sort of cleared up what we were talking about. And oops, I noticed my screen here messed up. Hopefully you can see it again. All right. Now there's a lot more to say, but I wanted to get into, so a student asked me about sinusoidal functions. Remember that the domain of sine and cosine is all real numbers. And it goes from negative infinity to infinity. And the range of sine and cosine is the interval -1 to 1. So those are considered to be the sinusoidal graphs. And in both graphs, the shape of the graph after 2 pi, as we said, it begins repeating after 2 pi. Indeed, since in reality, any coterminal angles will have the same cosine, sine and cosine values. And you can then conclude that the sine of theta plus 2 pi is really equal to the sine of theta. And the cosine of theta plus 2 pi is also equal to cosine of theta. So in other words, if you were to shift either graph horizontally by 2 pi, you have a resulting shape and it would be identical to the original function. That's the takeaway from this. And sinusoidal functions are a specific type of periodic function. And we already said that the period is 2 pi for both the sine and the cosine function. So we have kind of a situation where if you think about sinusoidal graphs, one thing that typically comes to mind for a lot of people doing modeling and examples is the London Eye. And I remember I was very opposed to the London Eye. I thought it was an eyesore. Really, I did think that. And it annoyed me. I don't know why, but it for some reason I was there when the whole thing happened. But anyway, the London Eye it's really a huge Ferris wheel, and it has a diameter of 443 feet. Yes, I know, 135 meters for all of you internationalists out there, but it's really 443 feet if you use the imperial system. And in London, and it completes one rotation every 30 minutes. So when you look at the behavior of the London Eye, it's clear it actually completes one cycle or one revolution And then it repeats this revolution over and over again. And that's an example of a periodic function because the Ferris wheel repeats the revolution or one cycle every 30 minutes. So we say that the period of it is actually 30 minutes. So the one way you can look at this is to do an application problem. So what if I asked you for a typical sinusoidal problem would be what is the amplitude of the equation f of theta? This time I'll try to put in the symbol in there. I think I had it. It worked out. All right. F of theta, we're going to say is equal to 7 times the cosine of theta. And then it would say something like, typically, sketch the graph. Well, in this case, we need to understand a few things. When you want to find the amplitude, if you get a question like that on a test, my dear subscriber, we have to break it down using a formula. And in general, for a cosine function, we have f of theta equals a times the cosine of theta. So the amplitude is the absolute value let's put it in everything. So the amplitude is the absolute value of A. And that represents, remember we talked about earlier, the maximum vertical distance from the function's midline, usually the x-axis, to the peak or trough of the wave. So in this case, in this example, we have 7 cosine of theta. So the amplitude is the absolute value of 7, which is 7. That's the easy part. Now, in terms of the graph, you're going to, well, you have a cosine, so it has to resemble a standard cosine wave, but you now have an amplitude of 7. That means that the peaks of the wave are going to reach 7, and the troughs will go down actually to -7. So since the period is 2 pi, one period goes from 0 to 2 pi, your key points for cosine would be as follows. If you have a table of values, and I did the table of values earlier, see if it comes up. All right, so here are the table of values. At theta equals 0, then it's going to be 7. At pi over 2, then it's 0. At pi, -7. At 3 pi over 2, 0. And then it goes back 2 pi, 7. So if you were to sketch this, if you were to use I don't know if they allow you to use, I would imagine they allow you to use a graphing utility. I used a computer for this, but it kind of looks sort of like, let's see if I can up. Something like this. All right. So you can see here 7 cosine of theta. The amplitude, we have the dashed red lines, and that indicates the maximum and minimum values the function reaches, well, 7 to -7. And the function completes one cycle over the interval 0 to 2 pi, right? That's one cycle, right? So hopefully that makes sense. Okay, another problem you might see that let's say you have something like Sometimes they ask you about midline. Now, the center, when you talk about the center of a sinusoidal function, the value is that the function oscillates above and below. And that's called the midline of the function. And it's really, you can represent it by a vertical shift in the equation. Right? So like if you have f of theta equals cosine of theta plus something plus k, then the midline would be y equals k. Right? Hopefully that makes sense. All right. I'm trying to think of another question that somebody had asked me about. So we talked about midline, amplitude, and period, right? What if I gave, so let's do one like that. What if I asked you determine or find the midline, amplitude, and period? We'll do f of t we'll do 3 times the sine of 2t plus 1. All right, so think about it for a moment, pause the video, and then we'll talk about it. All right, so now that you've paused the video, the amplitude here is represented by the absolute value of 3, which is 3. The period has to be 2 pi over b, right? So 2 pi over, it's really 2 pi over 2, right? So 2 pi over 2 equals pi. And the period is going to be 2 pi over b, which is 2 pi over 2. And that, of course, gives you pi. That's the period. And now the midline here is the plus 1, right? So that would be g of t equals 1. All right? So the amplitude, the midline, and the period, when you combine it with vertical flips, it's enough to allow you to write equations for a large number of sinusoidal situations. All right, now a practical application would be as follows. They give you a graph, right? And it would say something like, write an equation All right, so the graph that they're referring to, this came up on one of the Common Core tests. Let's see if I can pull up the graph somewhere. All right, they gave a graph like this, and it says, write an equation for the sinusoidal function of this. Well, have a look at where the graph oscillates. The graph is oscillating from, you have a low point of -1, and it goes all the way to a high of 3. So you have a midline here, of course, of 1, y equals 1. It's halfway between. So the amplitude here has to be 2. It's we have a distance from the midline to the highest value or lowest value of the graph, right? So that would be the amplitude. The amplitude would be 2. And the period of the graph, it goes all the way, it's actually 8. And you can measure this from you have the first peak when x is equal to, have a look at when x is equal to -2. So when x is equal to -2, to the second, x equals 6. That's your other peak. So since it goes all the way from -2 to 6, so your period is 8. So the stretch or compression factor you have to use, we have to use 2 pi over p, right? So it's 2 pi over 8. And That's really pi. You can reduce it to pi over 4. All right. And when you have x is equal to 0, you're at the mid. This graph is at the midline value. So that tells you that the graph can most easily be represented as a sine function. Why? Because if the graph then decreases, this has to be a vertical reflection of the sine function. So if you put this all together, we can label it as a function, f of x or f of t in this case. I'm going to use t for time. So f of t is equal to -2, right? That's the first, the peak here, -2, and we said that the period, right, is the compression factor was pi over 4. So you could do -2 sine, and you have pi over 4t. And we have +1. Right? If you have any questions, please let me know in the comment section below and I can clarify more. But now, if you have this idea, you can now be ready to answer the Ferris wheel problem, right? We talked about the London Eye. So typical question would be something like, we have the London Eye is 443 feet, right? If we put it together, if we put an equation for it, let me give you the info first, though. I've been having so much trouble with my screen. But here's a summary of it, right? You have a diameter of 135 meters, and it completes, right? And it's asking you, riders board from a platform 2 meters above the ground. Express a rider's height as a function of time in minutes, right? Well, if the diameter is 135 meters, the wheel has a radius of 67.5 meters. So the height will oscillate with an amplitude of 67.5 meters. Now, passengers, it says, they're going to board 2 meters above ground level. So the center of the wheel has to be, we have to add this 67.5 plus 2, right? So we started out with, now we have 69.5 meters above the ground level. So that's the midline. The midline is going to be 69.5, right? And so the wheel, we said, takes 30 minutes to complete 1 revolution. So the height is going to oscillate with a period of 30 minutes. And since the rider boards at the lowest point, the height is going to start at the smallest value and increase. It's going to kind of follow the shape of a flipped cosine curve. So if we put everything, all this information together, we can have an amplitude of 67.5, right? So you want to get into the habit of putting all the information so that you can create your expression. So the amplitude is 67.5. The midline is 69.5. And the period is 30. And if that's the case, so the shape is going to be negative cosine. And in order to get your period here, since we said it was 30, it has to be 2 pi over 30. And of course, this can always be reduced to pi over 15. Okay. And so now we put this together and create an equation. So an equation for the rider's height, you would have h of t And you now have negative 67.5 cosine times pi over 15t plus your midline, 69.5. So I hope, I mean, there's a lot more, but I hope that this was sort of functional for those of you who have a test this week. Some of you asked me. And I hope that this video serves as your emergency go-to for that. Thank you for watching. If this was useful, as I always say, please subscribe, continue to assist me in making this channel better and better and sharing mathematics with a wide audience, because as I've always said, you're being deprived. You are being you're being abandoned by a system that has failed. So I look forward to more videos with you. Thank you for watching.